Hi class, welcome back. We're going to finish up chapter 6, part 3 today. Specifically, we'll be talking about thunderstorms and a phenomenon known as El Nino Southern Oscillation, or ENSO. So let's start with thunderstorms. So thunderstorms are basically storms that develop when we have warm, moist air rising, forming cumulus clouds, and allow them to continue to grow by pulling in more moist, warm air. That air will rise, release its latent heat, pull in more. That air will rise, release latent heat, so the cloud will continue to grow. In phases, we'll see these grow from the cumulus cloud stage, pretty harmless, to the mature stage where we get both updrafts and downdrafts of air at the same time, developing moisture droplets from condensation or ice crystals from deposition. So we get the formation of ice and water in a chamber of air, some going up, some going down. So we have updrafts, we have downdrafts, and they're going to be in contact with each other and actually click little parts of these water molecules off of each other. So some of the electrons get knocked off of some of these molecules. And what that tends to do is put positive charges, so that's an area where they don't have enough electrons in some portions of the cloud, and negative charges where we have too many electrons accumulated in other parts of the cloud, and those will then have to even out, sort of like a battery. And that's the spark or the flash we see of lightning when this charge is evening out. And it can be from one part of the cloud to another part of the cloud. It can be from one cloud to another cloud. It can be from the cloud to the ground, as we'll see in a few minutes. Once the cloud has run out of energy, is run out of that warm, moist air rising, then we'll see that downdrafts prevail and the storm is basically becoming done with. It's in its dissipating phase. So the three phases of thunderstorm development would be the cumulus stage, the mature stage, and the dissipating stage, with the mature stage being the most dangerous. So here's a nice picture of lightning. You can see that. You wouldn't want to be anywhere near that. That's over 50,000 degrees Fahrenheit, hotter than some parts of the sun. So here's a little diagram of those updrafts and downdrafts and updrafts and downdrafts. We've approached this subject once before when we talked about the formation of hail inside cumulonimbus clouds. So another thing we see in cumulonimbus clouds, we see hail, heavy rain, lightning, thunder. Now again, lightning is the visual component of what you see, that flash of light, and thunder is the noise of the displacement of those air molecules from that flash of light emanating out. And it takes a little while for that noise to reach us compared to the light reaching us. So it takes about 1 mile for that sound, sorry, it takes about 5 seconds for that sound to travel to us for every mile of distance. So again, here's those three phases. Cumulus stage, mainly updrafts. The mature, the most dangerous phase, updrafts and downdrafts, when we get the most lightning, heaviest rain, etc. And those lightning flashes, and you can hear the thunder. And then later, the dissipating phase, when the storm is pretty much run out of energy. So remember, it's geography. Where do we get these thunderstorms? Well, you need to have some heat and you need to have some moisture. Now, it might be counterintuitive, but we get more lightning over land than we do over the sea. So lots more lightning over the land than we do over the sea. That shouldn't be too surprising because land can heat up considerably more than what the ocean surfaces or the seas can warm up. So there's our heat component. And when the air above the land heats up and rises, it can suck moist air in from any adjacent moisture source like a sea or an ocean. We do see lightning over the seas, just not as much as we see over the land. Now, the axis on the bottom here runs from 60 degrees north to 60 degrees south. I'm going to have to lock myself out of here in a second. There we go. As you can see the diagram a little bit more full now. So from 60 north to 60 south, the middle of that right here, 0 degrees, that's pretty much where we see most of the lightning and thunderstorms. So very close to the equator. That shouldn't be too surprising, right? Because what does the air do at the equator? Tends to rise, and that rising air, we know it's moist air at the equator. It's going to give us a lot of release of condensation. and latent heat, and it's going to be quite conducive to thunderstorm development. Do you notice that as we get north of 60 degrees north towards the Arctic, or south of 60 degrees south towards the Antarctic, we don't really see thunderstorms? What's the missing component there? The heat. We just don't have enough heat in the air to develop thunderstorms beyond those latitudes. We can see here geography of thunderstorms, that most of our thunderstorms are centered around the equatorial regions. If we look at this in terms of actual lightning flashes, again, we can see that we get heavy concentrations near the equator in South America, in equatorial Africa, and throughout Indonesia and surrounding countries. We also see that we do get thunderstorm activity in the United States and other North American destinations in the summertime. Same with Europe, mostly summertime. Australia, mostly their summertime. South Africa, mostly their summertime, etc. So we need that heat source. At the equator, we have so much of it that we get quite a bit of activity year-round. If we look for ground central, I would say equatorial Africa would be ground central for lightning strikes. You want to go study lightning, that's where you want to go do that. This is what lightning clouds look like from the top. These tops of cumulonimbus clouds would be thunderstorm clouds. So we get about 100 lightning flashes across the planet in any given second. So within that 1, 2, 3 seconds, 300 lightning strikes somewhere across the planet. So it's quite frequent. And as we just saw, some places more than others. So again, because of the upward and downward movement of water molecules within the cloud, or especially ice molecules, ions get knocked off of the water molecule, and some areas become depleted of ions, of electrons, and some places get extra electrons, and that evening out within the cloud, or from this cloud to another cloud, or from the cloud to the ground, would be considered lightning. The purpose of that lightning is to even out those charges. And again, sometimes that can be within the cloud, sometimes from the cloud to the ground. And to tell you the truth, it's kind of like a ladder effect from the cloud to the ground, back to the cloud, etc. Little step ladder effects. Where's the one place you probably don't want to be during a thunderstorm or lightning storm? Near a tree, because if that tree gets hit, it would get instantly, well, the water inside the tree would get vaporized. It's contained by the tree's cell structure. Pressure would build, it would explode outwards, and if you're anywhere near that tree, you basically get shredded by pieces of wood. So don't do that. If you get struck by lightning, not a good thing. 54,000 degrees Fahrenheit, not good. So don't get struck by lightning. Promise me. Okay, you can tell we're being pretty brief here. The last topic that we're going to cover on the chapter is something called El Nino Southern Oscillation, and that's abbreviated quite readily as ENSO. So again, El Nino Southern Oscillation. And the El Nino portion refers to how the surface temperatures of the sea, which we call sea surface temperatures, they get a little bit warmer than average, a little bit cooler than average, a little bit warmer than average, a little bit cooler than average. And we can monitor where the ocean temperatures are getting warmer than average, and we can also monitor where they're getting colder than average. And that change in sea surface temperature across the equatorial Pacific is referred to as El Nino. Specifically across the equator in the Pacific Ocean, and if we look at one side of the Pacific versus the other, we can monitor these changes. I'll explain that in just a second. Now, the southern oscillation refers to changes in surface air pressure from one side of the Pacific Ocean to the other side of the Pacific Ocean across the Pacific. So whatever normal or average atmospheric pressure is over time, sometimes we'll see a period where it's a little bit lower on one side of the Pacific, and another time of the year, it could be higher. Or on another year, it could be higher pressure than normal. So, El Nino, southern oscillation, oscillating warm water buildup or cold water upwelling along the coast of the Pacific Ocean, either on the tropical Pacific side or on the side of Asia. Again, let me explain that in here. I need a map to be able to do that. First and foremost, remember that the trade winds, both the northeast trade winds and the southeast trade winds, typically blow from the east towards the west. So across the Pacific, they're going to blow from the west coast of the west coast of South America, which is the eastern portion of the Pacific Ocean. And they're going to blow from there towards the western Pacific, which includes the east coast of Eurasia. Let's take a look at that in just a second. Before we do that, I want to explain that under normal conditions, we would have off the coast of Australia and New Zealand warm sea surface temperatures, low atmospheric pressure, and some summertime moisture. And normal conditions for the eastern Pacific off the coast of Ecuador and Peru, we would tend to get high pressure, sinking air, drought conditions, and that's going to allow water to upwell. We need a three-dimensional map to show that clearly. But let's look at what I'm just talking about. Here's the Pacific Ocean, okay? And across the equator, we can see that this is the eastern Pacific, and that butts up against the Isthmus of Central America and down into South America. So we're looking at the eastern Pacific meeting the west coast of the Americas. Over here we have the western Pacific, and that bumps into New Guinea, lots of Indonesia, northern Australia. So this region would be referred to as the western Pacific, and this region would be referred to as the eastern Pacific. And the trade winds will typically blow from the Americas towards Asia, from the Americas towards Asia. What that's going to do is basically drag the water across the surface from the eastern Pacific towards the western Pacific. And because the whole time this water is under the equatorial sun, this water is going to get warmer and warmer and warmer. So the water starts off pretty cold and ends up pretty warm. Now, one of the reasons it's starting off as cold is that cold water currents are coming down the coast of the Americas, and they're coming north from South America up towards the equator before they make their journey across the Pacific. Not only that, but as the water pulls away from the coast of the eastern Pacific, cold, cold, cold water from down deep in the coastal waters here comes back up to the surface and then across the Pacific surface. So it's pulling water up from deep below, and that water from very deep is quite cold. So it starts off with very cold water. In fact, if you were in the Galapagos Islands, somewhere over here, the Galapagos Islands, if you were snorkeling there, the temperature of the water might be about 64 degrees Fahrenheit. Not very warm for the equator. But as that same water comes to the surface and then gets dragged across the surface under the direct ray of the sun, that water is going to get warmer and warmer. By the time you get over towards Indonesia, that same water might now be 86 degrees Fahrenheit. So very, very, very warm water over here. So under normal conditions, we got warm water in the Western Pacific. And warm water is going to evaporate some of that warm water into the air, making the air warm and moist. And that warm, moist air is going to want to rise. So we've got low pressure off the Western Pacific. Low pressure. In fact, we measure that quite often in Jakarta, Indonesia. And Jakarta, Indonesia is probably right about here on this map. So typically, we would get low pressure in Jakarta, Indonesia. Low pressure, rising air, lots of thunderstorms out here. Conversely, in the eastern Pacific, with that cold water, that's going to chill the air down, make the air want to sink. So we get high pressure over here, high pressure, sinking air, not much in the way of rainfall. And the air would blow from the high pressure across the Pacific towards the low pressure. All makes sense. That's under normal conditions. By the way, the benefit of that cold water coming up across the coast here, from that upwelling of cold water, is that cold water contains a huge amount of nutrients. And when those nutrients start to hit sunlight, then we're going to see a bloom of algae and phytoplankton, and then lots of fish gobbling up the plankton, and large fisheries develop off this coast during normal conditions. Just to reiterate, again, hard to see on this map, but the Americas western coastline is outlined here. So the Pacific Ocean is over here. And we see the northeast trade winds blowing this way, the southeast trade winds blowing this way, dragging that water across the Pacific. So by the time we get over to the western Pacific out here, we have pretty warm water and low pressure. Again, normal trade winds. Now, so we just discussed normal conditions. Every now and then, about every 2 to 5 years, we see that the trade winds, they strengthen for some reason. They get stronger, and they're going to exaggerate everything that we just talked about. So all the stuff we talked about in terms of normal conditions, we're going to see like those same conditions on steroids when it comes to La Nina conditions. So our second set of conditions is referred to as La Nina. So the trade winds get stronger. Now we see the water pulling away from the coast of the Americas, even more so towards the Western Pacific. So we get even more warm water over by the coast of Indonesia and Australia. We get even more low pressure off the coast of Australia and Indonesia. So remember, normal conditions, average trade winds, average pressure. During La Nina conditions, what is normally low pressure in Australia and Indonesia become even lower pressure than normal. And that means even more rising air, even more rainfall. So we get lots and lots of even flooding events during a La Nina condition off the coast of Indonesia and Australia. Now the Americas, on the other hand, we typically have sinking air and high pressure, dry conditions. They're going to be even drier conditions during a La Nina event. So La Ninas are just the same thing as normal conditions, but they are exaggerated conditions. So what does that do? Here's 1997. It sounds like a long time ago, but this is a good example. So a La Nina in early 1997 dragged so much of that water from the eastern Pacific towards the western Pacific, and that water just spread out not only to the north and to the south, but also gets pushed downwards by these strengthened trade winds, pushing that water down. And this whole area over here was experiencing warm sea surface temperatures, very low atmospheric pressure, lots of rainstorms, and lots of flooding off the coast of Indonesia and northern Australia. Now, again, about every 2 to 5 years, something funky happens. We still haven't figured out the mechanism that makes it all happen. We're trying to figure that out now. But the trade winds get weaker than normal. So they die down. Now, as they die down, that water that had been pushed down deeper in the western Pacific starts to come back up towards the surface and flow back in a eastward direction away from Australia and New Zealand in the western Pacific and towards Peru and Ecuador in the eastern Pacific. And as that water migrates across the ocean and gets towards the west coast of the Americas, it's bringing with it not only that warm sea surface temperature, but also the thunderstorms and the rain that go hand in hand with it. So we get low pressure in the eastern Pacific. So it's a flip-flop. Under El Nino conditions, we now have low pressure in the eastern Pacific, rainfall in the eastern Pacific, warm sea surface temperatures in the eastern Pacific. So that is definitely opposite of what we would normally get. Now, at the same point, Australia and Indonesia, typically they'd have low pressure. Now they get high pressure. Typically, Australia and New Zealand would have, Australia and Indonesia would typically have low pressure. They get high pressure. Typically, they would have rainfall. Now they get drought. And if there's any kind of brush fires, those brush fires go out of control. They also, instead of having very warm sea surface temperatures off the coast of Australia and Indonesia, they would get cooler sea surface temperatures compared to normal. So look at an El Nino here, late 1997. That warm water that earlier in the year had been pushed down and out in the Western Pacific has now migrated all the way across to the Eastern Pacific off the coast of the Americas. And that only happens during an El Nino event, such as this one in late 1997. And if all the warm water is over here, now we have thunderstorm development off the coast of South America. We get low pressure. So the low pressure has switched from the Western Pacific to the Eastern Pacific. We get lots of rainfall out here. Also, what we see is there's no room for this cold water to upwell against the coast of the Americas with all those nutrients. So it's very poor for fishing during an El Nino event. The Peruvian fishermen were the first to name this event. They named it because it would arrive just around or just before Christmas time. So they named it like the Christ child, El Nino. So an event that would bring a change in the amount of rainfall, in the pressure, in the fisheries. So actually pretty poor fisheries or pretty poor fishing during an El Nino event. So the fishermen would have to go further out into the ocean or they'd be catching a different type of fish. So we can see here warmer water than normal off the coast of the Americas, and that would be an El Nino event. Now, the reason I'm showing this diagram is we are way up here. We're up in Southern California. We are nowhere near the equatorial Pacific. An El Nino, Southern Oscillation, is a tropical Pacific event. But during big El Nino events, that's going to put a big blob of warm water off the coast of the Americas. It's going to give a big blob of warm air. Our typical air currents are going to have to flow around that, so the jet stream gets a bit impacted by this, gets diverted by it. But also, whenever we have our big winter storms, remember those mid-latitude extratropical wave cyclones during typically January, February, March into April, when our storms come through, they suck moist, warm air, maritime tropical air from the Pacific in advance of those storms. So the cold front is the border of the cold air coming down. Well, that border leading up to a low pressure center would suck up some of that moist air. So in a big El Nino event, we may get more moisture in our Southern California winter storms. It's often the case, but not always the case. For instance, 1997, this was a very typical scene in our winter, January, February, March, and April, 1997. Lots of rainfall and lots of subsequent mud flows in Southern California. That big blob of warm water sitting off in the Pacific, some of that air was sucked in towards Southern California and became part of our rainfall regime. Again, a quick overview here. Here we have the Eastern Pacific. Over here will be the Western Pacific. And during El Nino and normal or neutral conditions, the low pressure would be off the coast of Indonesia and Australia in the Western Pacific. That air would sink down off the coast of Peru and Ecuador in the Eastern Pacific, and we'd have airflow going across the Pacific from east to west. Normal conditions and warm conditions, the neutral conditions, and La Nina conditions would fall into this regime. El Nino conditions, on the other hand, would be this diagram down here. So this upper diagram would be for neutral and La Nina conditions. My apologies for saying that differently earlier. During El Nino conditions, we have a flow of air moving from the west towards the east of the Pacific, rising over the eastern Pacific. So El Nino conditions give us rainy conditions, typically, in Ecuador and Peru during El Nino conditions. So the last slide here is showing recent El Nino data. Now, we define an El Nino as when we have average or 3-month average sea surface temperatures being 0.5 degrees Celsius or more warmer than normal. And for a La Nina, 0.5 degrees Celsius or more colder than normal. And in between, so from 0.5 or less than 0.5 warmer than normal to 0.5 Celsius colder than normal, within that range, we would call that a neutral or normal year. So for the period from the 2000 to 2001 winter season through the 2019-2020 winter season, I want to look at this column here, January, February, March. That's when we get most of our rainfall. And looking at that, let's see what kind of impacts we would have. So basically, we have, I'll count these out, 1, 2, 3, 4, 5, 6, 7. 7 years we would consider to be La Nina conditions during our peak winter rainfall season. For El Nino, 1, 2, 3, 4, 5, 6, almost the same. So 6 El Nino January, February, Marches. And for neutral or normal conditions, 1, 2, 3, 4, 5, 6. So looking at this for Southern California, during the peak of our winter season, we've experienced almost the same number of normal conditions, El Nino conditions, and La Nina conditions during our last 20 years or so. In essence, there's about an equal chance each year that we're going to experience these various conditions that originate in the tropical Pacific but do have impacts for us. Now, typically, again, when we have a big El Nino, we should expect to get, or our possibilities are that we will get wetter conditions or potentially wetter conditions from the storms that pass our way. There's too many variables to make it that simple. But as a general rule, we have a more potential for larger amounts of rainfall during our winter storms when we have El Nino conditions. When there are La Nina conditions, the potential should be less. But again, the jet stream gets diverted, all kinds of variables come into play. There are big high pressure blobs that have existed in the Pacific Ocean, blocking some of our winter storms coming through. So lots and lots of variables, but overall, we can look at the impacts as potential impacts. Now, if you lived in Peru or Ecuador, whenever you had an El Nino, you're probably going to get wetter conditions than normal. And during that same El Nino condition, if you lived in Australia, Australia, Indonesia, or probably New Zealand too, to be honest, you'd probably get drier conditions during an El Nino year. During a La Nina year, Peru and Ecuador probably going to get drier conditions than normal, and Indonesia, Australia, even wetter conditions than normal. So I hope that kind of gives you an idea. Please feel free to go back through the regular slides, but this should be a quick overview to enable you to understand it just a little bit better. Okay, thanks, take care, be well, be safe.